One of my favourite astronomers of all time is Johannes Kepler. His three laws of planetary motion form the bedrock of many scientists' work that came after him, including the likes of Isaac Newton himself. So when I saw someone trying to dispute one of Kepler's planetary laws, I simply had to step in. Hello all and welcome along to another episode of Tinfoil Tuesday with me, Simon Dan. Thank you very much for joining me. Right, back to today's video, which is all about a man named Geoffrey Wolynski trying to debunk Kepler's second law. Now you may remember Geoffrey from a previous video. Here's a quick clip if you haven't seen him before or don't remember.
So basically, they're self-induced heat pumps which pull the vacuum material from the vacuum onto itself, or the heat from the vacuum onto itself. Mind you, the vacuum is a hell of a lot colder than the object they're trying to form. It's very, very, very weird.
Well, today he thinks that Kepler's second law is faulty. How very dare he? Before we dive in, let's have a quick look at exactly what Kepler's second law of planetary motion is. A line segment between a planet and the sun sweeps out equal areas during equal amounts of time. Now what that means is, if you take a given length of time, such as a month in this image here, a planet will sweep out equal areas from given radius vectors. Now this is essentially saying that planets move at different speeds along different points in their orbit. Faster when closer to the sun and slower when further away. Now it can be proven mathematically every single time. You just can't refute it. So let's join Geoffrey as he tries to debunk it.
Kepler's second law, and I'm going to get a lot of heat for this one, but Kepler's second law is incorrect.
Well, it's not, but please continue.
It's as simple as it goes. Hello, Celeste. For planets, you recall Kepler's second law was his discovery that angular momentum is conserved. For the planets, as they go around the sun, their masses don't change, but their distances from the sun do. As they get closer to the sun, the distance gets smaller. They orbit faster, which means they pick up velocity. The product of these two quantities remains unchanged, thus angular momentum is conserved. But Kepler's law is only true in a very perfect case. And that perfect case is if the planets do not evolve.
If the planets do not evolve? What, you mean like Pokemon?
Meaning lose mass. That mass is lost from the object. So mathematically you can go, well, here's the planet, it's perfect, and it's idealized as something that doesn't lose any mass. It covers distance 1 and distance 2 in an equal amount of time. So say this is 1 month and this is 1 month, and when this one orbits really far out, this entire area, if you measure it out, will match the same amount of area as this area right here, because this one will be moving a lot faster, though it's a lot closer.
The thing you have to remember about these diagrams though is that they are greatly exaggerated. And that's done to make you understand the concept. The eccentricity of Earth's orbit is 0.01671, which means it's almost a perfect circle. Now, an eccentricity value of 0 means a perfect circle. However, even with this very small eccentricity value, the distance to the sun for the Earth changes throughout the year by as much as 5 million kilometers. Now, Mercury is the planet with the largest eccentricity value at 0.206. Now, this means for Mercury, the distance to the sun differs by up to 23 million kilometers, passing as close as 47 million kilometers to the sun and as far away as 70 million kilometers to the sun. The most eccentric orbit in the solar system, though, belongs to a moon of Neptune. Nereid has an eccentricity of 0.749. Now this means that it passes as close as 1.3 million kilometers to Neptune, but as far as 9.6 million kilometers at its furthest. But in terms of Earth's eccentricity, that diagram is very much exaggerated.
So this area will match this area, given these two are in the same amount of time. But this is false because, number one, the planet, the evolving star, loses mass.
Jeffrey thinks that planets are old stars, by the way. Now, the Earth actually gains and loses mass throughout the course of a year, but there is a net loss of around 55 million kilograms per year. Now, to put that in perspective, that is 0.00000000000000092% of its mass per year. Now that number is so embarrassingly small that at that rate the Earth would take 100 quadrillion years to lose all of its mass. The Earth is only 4.5 billion years old. The mass loss is, for all intents and purposes, negligible.
So if it's out here, it's probably going to retain the mass. If it's up close, it's probably going to be losing mass a lot faster because of the heat from the host.
He's taken this diagram way too literally. The difference in temperature between the closest point to the Sun and the furthest point for Earth is again negligible.
Ripping it apart. So it could orbit at a certain time, but each time it ticks around and it hits this area, it's going to lose that mass. And these two amounts of time are never going, or you could time this perfectly, but this will shrink for each time it gets close. So you have more and more and more shrinkage as the object evolves.
Again, there is no evidence to suggest that a planet evolves, and certainly none that it used to be an old star.
Basically, that's it. Kepler's law is an idealization. It's like the perfect gas law, PV equals nRT. It's like the perfect triangle, all the inside angles equal 60 degrees. It's an idealization. It's not perfect. Now, in that sense, it's incorrect. It's wrong.
Except for the fact that practically, physically, and mathematically, it's not.
It's mathematically useful, but for as correct as the math is, the physics doesn't pan out. Especially when you stretch this orbit out over millions of times, the wrongness will expand outwards, and you'll see that Kepler's law is just a mathematical trick, if you will.
The wrongness will expand outward. Real scientific conclusion there, Jeffrey. Now, this is basically an attack on Kepler's second law of planetary motion based on astrophysics that you have entirely made up.
Make people believe that they really have a firm beat on things. All right, y'all. Later.
Well, there we go. A very interesting take on Kepler's second law there by Jeffrey Wolynski. Entirely wrong, of course, but still interesting. But there we go. A lovely Tinfoil Tuesday there, all done and dusted for another episode. Thank you so much for watching. As always, it's truly appreciated. If you enjoyed today's episode in particular, please do consider subscribing to the channel and liking this video as well. And if you really liked it, please do share the video too. I've been Simon Dan. Have yourselves a cracking week, and I'll see you all on Friday, where we go take a look at part 2 of the Level With Me documentary. Can't wait for that one. See you then.